let's get into it. Should be good. I'm sharing to Google. That should show up. Everyone's good. Let me know. You could all see that, right? Just making sure.
And I just want to mention one quick thing. Alex mentioned that we happen to be having the event same day as the GopherCon Europe. So maybe we're losing some people to that event.
Oh yeah, I forgot about that.
It was the last day today, so I think it ended. But yes, I saw like last week. I connected the dots and saw that we overlap with GopherCon Europe.
There's always something going on. Cool. All right, I'm ready to rock when you are then.
Yes, please. Let's start.
Awesome. Well, thanks everyone for joining. Again, we are live on YouTube, so if you have questions, put it in the YouTube chat. We're probably operating on a little bit of a delay here, so when you have a question, just know that like by the time you ask it and the time we see it, it's probably a delay. So just be specific in what your question is. Cool. But my name is Matthew Sanabria. I'm here to give you a talk on pointers and interfaces in Go, what all Gophers should know. I actually created this talk for another Go group that I was a part of to present to them like more information about pointers and interfaces and all that stuff. So I have a bunch of slides here. There are a lot of slides, but they're pretty like minimal, so we'll go through them kind of quickly-ish. But awesome, let's get started. So who am I? Well, I'm Matthew Sanabria. I'm currently a staff site reliability engineer at Cockroach Labs. You can find me at pretty much all of the socials using my tag at @sudomateo. You'll find me on Twitter, LinkedIn, all of that good stuff there. I'm in the US, so you guys are feeling my need. Yes, exactly. We try to make sure the US gets some content too. So let's talk about pointers, right? This is the first. We'll start with pointers, and then we'll dive into interfaces because we kind of have to understand a little bit about pointers before we even dive into like anything about interfaces. So what exactly is a pointer? When we say this term all the time, right? Use a pointer, use this, use that. What is a pointer exactly? Well, it's really under the hood, just some sort of object or variable, right? That stores a memory address. That's literally all it is at its core, right? Something that stores a memory address. There can be things at that memory address, but we don't really know or care what that is at this point. When we have a pointer, we just have basically a memory address, right? But what is like, if you have these different variables in your program, what does the memory layout actually look like, right? Because we have variables that store values, we have variables that store pointers, we have all of these variables that we use throughout our programs, but like, what does it actually look like in memory? Well, let's take a look. So I have this program here, right? It's pretty simple. We just declare a variable called age. We give it the value 30, and then we print the value of age, and we also print the address of age, or its pointer, right? So if we were to run this code, we would get something that looks like this in memory. We'd get a memory layout that looks just like this. And you can see here that your memory in your computer has what are called addresses. And those are those top like hex numbers at the top, right? Each of those has a memory address, and you can store things in that memory. But we declared in our program a variable called age, and we gave it the value 30. So somewhere in memory, there's an address that's holding the age value, the value for the age variable, right? In this case, it's holding the value 30, and the variable that it's holding it in is called the age variable, and that's stored at this memory address somewhere in memory. This is essentially what it looks like. But when you have a pointer to this memory, you're not actually looking at the 30 that's in that box. You're looking at the address of that memory box, right? That memory address. So when you have like the ampersand age to say, give me the pointer to age, you're looking at this address here in red, right? So this is essentially what's happening with that program under the hood in memory. Let's look at a different example though. So the previous example, I had the variable age that stored the value 30. In this example, I have a new variable called new age, and it's not going to store a value like an integer. It's going to store the address of the age variable, right? So I have age storing the value 30, and then I have new age that's storing the address of age, or pointer to the age variable. And again, printing out the value at new age, the pointer of new age, and the dereferencing of new age, which is with this star syntax. What does this actually look like in memory? Well, it looks something like this. You still have that same address. You still have that same memory address that's storing the raw value 30 for the age variable. But now we have this new age variable, and its value is actually a pointer to the age variable. So it's kind of like a little bit of an indirection here. But when you look at new age, the value that I care about is this red value in the box here. But if I were to look at the address of new age, I'm getting its memory address, right? So it's not the pointer that it's pointing to, but its own address in memory. And actually, if I go forward 2 slides, you'll see exactly kind of how this looks like. So you have age storing 30. You have new age storing a pointer to age. And then when you use the dereference operator, which is the star, what you're doing is essentially following that pointer and saying, hey, I know that my value is a pointer, right? This B4000. Follow that pointer and find the value that it stores. Oh, it happens to store an integer? Great. So when you do this star new age syntax, you're following that pointer or dereferencing it back down to whatever value is stored in its location. So this is essentially how this looks in memory. And I know this may be a little bit like, wait a minute, Matt, what's happening here? There's like so many addresses on the screen. It'll make more sense as I continue to show more information here when we look at the call stack. So let's look at the call stack next. In Go, or technically in any programming language, as you call functions, you are creating new call stacks, right? Or new stack frames, technically. And those stack frames have memory, and they store like your functions, local variables, and all that stuff. But in these functions, you're going to be passing values down the call stack, and technically, you're going to be returning values up the call stack. So let's follow that and see what happens in these programs. So I have another program here. Simple program again. I have age that's storing the integer 30. I have this increment function here that takes an integer and then increments it by 1 and does nothing, right? It doesn't return the integer back. It doesn't do anything. It just takes an integer, increments it, and then does nothing. What does that look like on the call stack? Well, as soon as I call the increment function, this is what my stack kind of looks like, right? You have a function main, and the age value inside has the value 30. Then it calls a new function called increment, which creates a new stack frame. And just after I enter the increment function, this is what it looks like. It has that value, the variable x with the value 30. Right after I do the plus plus operation inside increment, the local variable x has been incremented by 1. So now it's 31. And then when I return from increment, what happens? Well, the stack frame for that increment function gets basically deleted from memory, right? Gets erased, it goes away. And I'm just left with my original stack frame for main, but you'll notice that the age variable has not been incremented, right? So going back to the code for a second, I had a variable that stored the value 30, passed it to this increment call. The increment call incremented the value, but the original variable age didn't see that increment, right? What actually happened here? Well, when you pass variables around in Go by value, right? When you don't pass a pointer, you pass a value. Those values are passed by value itself, right? They're copied to the function that you're passing them to. So in our case, going back a few slides, the increment operator, right? Or sorry, the increment function received its own copy of the age variable, and it happened to call that copy x in its code. Notice here on this stack here, we have 2 different addresses for these stack frames. These variables are 2 separate values in memory. They each get their own memory. They're copies of one another. So whatever I did to x can't possibly affect the age variable because it was passed by a value, right? It was copied. What if I were to update that though? What if I, instead of passing a integer to the increment operator, what if I passed a pointer to an integer, right? So basically the same code here. I have the age variable again. I'm calling increment, but this time I'm not passing the age variable directly. I'm passing a pointer to the age variable, right? I'm passing its address, its memory address, to the increment operation. Since the increment operation now is receiving a pointer, it's able to dereference that pointer, find the underlying integer that's stored within, increment it. What does that look like on the call stack? Well, it looks like this. When I call increment, right? As soon as I call increment, this is what my stack looks like, right? I have two stack frames here, one for the main function, one for the increment function, and this is what it looks like in memory. But you'll notice now, even though my main function has the age variable with the value 30, you'll notice the increment function no longer has a copy of the age variable. It has a reference or a pointer to the age variable directly. So you'll notice that the value here for X is the same as the stack, like the address for age above. Now I've given the increment function direct access to mutate my age variable. So when I call the plus plus operation in my increment function, this is what happens. Age gets incremented to 31, and my main function sees that happening. Now, when I'm about to return from the increment function and get out of there, the stack frame is destroyed. But since I passed a pointer to increment, the change that I made by incrementing the pointer has been seen by my main function. So the caller sees the update. It sees the mutation, right? So what's the behavior here? Well, when you have pointer parameters in your functions, which we did have in this case, right? We had a pointer to an integer. When you have those pointer parameters, they are passed by what we call a reference. Now, experienced gophers in the audience might be like, well, Matt, actually the pointer is a value. Yes, it is a value, but the value is a memory address, and we call that a reference to a memory address, right? So when I say here, when you have a pointer parameter in your functions, you're given the function that you're calling access to that underlying memory address, and it can mutate it, right? So that's kind of the way down, right? We've called functions down the call stack. We've increased our call stack, did some stuff, and returned. What about if we return values from the functions that we call? What does the path up look like? Well, it looks something like this. Again, kind of the same idea here. We have, and I can move this little Google Meet thing. Sorry, it's bothering me. We have the same idea here. We have a function, same concept. We have age that has the value 30. We have this new age variable that's going to store the return from the increment call. And I have that null variable here to satisfy the compiler. Otherwise, this would not compile. I like to give my code examples as compiling code so that if people want to look at it, they can do it. But you'll notice here, the increment function takes a value, like an integer, right? A value. It does not take a pointer. It takes a value. It takes that value, increments it, and returns the new incremented value. So in this case, even though the increment function is going to receive a copy of the age variable, it's going to increment that copy and return the modified value back to the caller. The caller will accept that in its new age variable, and it can do whatever it wants. So what does this look like on the call stack? Well, it looks like this. As soon as we call increment, this is what our stack looks like. We have the main function with two variables, age and new age. And you'll notice that new age is set to its 0 value, right? Because it's an integer, the 0 value for an integer is the number 0. So new age is currently set to its 0 value because it has not been assigned to yet. It's been declared, but not assigned to. We enter the increment function. X is now set to 30 because that's what I passed into the increment function. Then when we call the plus plus operation, right, when we increment the actual X, this is what the stack frame looks like now. X is now 31. And then we're going to go return that back to main. And here's what we're left with main. The age variable remains at 30 because we didn't touch that, right? And the new age variable is now 31 because that's the value we retrieved back from the function. Same concept, right? When you return values from your function, they are stored on the stack. Why? Because the compiler knows that when you're returning an integer from a function, it knows that it needs enough memory to store that integer. It puts that memory on the stack. If I go back a few frames, you'll see here that even though this new age variable has not been set yet, has not been assigned to yet, the compiler knows that it's going to hold an integer. So it can create a memory address on the stack for you to hold that integer. And then when the function returns, it's just assigning that returned integer to that value on the stack. So this is a function that's not actually like allocating on the heap, right? Because all of the memory here remains on the stack. What if instead of actually returning a value, right, like a concrete value, what if I returned a pointer from this increment function instead? So again, I have the same exact code here. Increment still takes an integer by value. It still increments that copy of the integer. But this time, instead of returning the integer that it incremented, we're going to return a pointer to the integer that I've incremented. So what's going to happen here? Looking at the call stack again, as soon as we call increment, this is what our call stack looks like. We have age storing the value 30, right? It's at one memory address. And then we have this new age variable, but since its type is going to be a pointer, its zero value is nil, because pointers with zero values are nil because they hold memory addresses, not like an integer or a string. They're a memory address. So at the time I call increment, the new age variable is nil, but notice it has its own memory address, right? This AE020. It has its own memory address. I pass the copy of age into increment. It gets its own copy. Then if I perform the increment, that local copy X gets incremented to 31. But now the fun part begins. I'm returning this back from the increment, and I want to store it in that new age pointer, right? I'm returning a pointer to X. So what's going to happen here? You'll notice that the memory address for this X variable is B4010, right? In the increment stack frame. What does that mean for the return? Well, my return value is just going to have that stored as its memory address. So you'll see here, this new age variable now stores that B4010 address. But wait, we just eliminated that memory address, right? Like going back one slide, we know that this memory address is going to get destroyed when the stack frame gets removed from memory, right? So if I'm storing that address in the new age variable, but it got destroyed because the stack frame is gone, how the heck does my program work, right? Didn't I just like remove the memory that I needed? Well, in this case, the Go compiler knows that it cannot possibly store this new age variable, right? It can't store the value of that on the stack, because if it did, it will get destroyed once the increment function returns. So instead, the Go compiler says that has to escape to the heap. So when you have a function that returns a pointer, right? If it allocates that pointer and returns it, then once you call that function and it gets, whenever it returns, if you still want to have access to the return pointer and you save that as a variable, it needs to go to the heap, because if it stayed on the stack, it'll get destroyed. This is what we call allocating in Go. And if you look at like, you can build your Go programs with like certain compiler flags that show you like what the compiler is doing, the decisions it makes. I forget the flags off the top of my head, but if you did look at some of your programs, you'll see that the compiler makes certain decisions, and one of the decisions that it logs says this variable escapes to the heap, right? That's what the Go compiler says. So whenever you hear a gopher talking about like, oh, that escaped to the heap or that's allocated, all we mean is the actual memory is not on the stack, it's on the heap. And that's an allocation. So that's what that means. So just keep in mind, when you are building your functions and you're returning values directly, or if you're returning pointers to values, think of the like implications of doing so, right? Because generally speaking, if you return a pointer, it's most likely going to escape to the heap unless the Go compiler can optimize that away. Cool. Excuse me. Cool. So let's recap what we just learned about pointers, right? Because I know I gave you a lot of information there. Okay, -m is the compiler flag. Thank you. Let's recap what we learned about pointers just now. So what does all this mean for us as gophers, right? Great. We know that Go has pointers. We know that Go has values. What does this all mean? Well, it means to just be aware of like the semantics that you're using when you are writing your own code. Are you using values or are you using pointers? Because the semantics that you're using have different effects depending on what you're doing. Here's a good table that I've came up with that shows the difference between using values directly or using pointers. When you use values, you get them passed by value, right? They're copied. Values are copied across functions. When you use pointers, they're passed by reference. When you use values, the returns are usually stored on the stack frame. And when you're using pointers, those returns are most likely going to escape to the heap unless the compiler, optimize that. Values can't mutate object state, but pointers can. Values also can't represent nil objects, right? You can't have a nil integer, but you can have a nil pointer to an integer, right? So if you need to represent like optionality, you would probably want to use a pointer. And if you have large objects that you're working with in your program, calling functions that copy that around to different stack frames can use a lot more memory than just passing a pointer around because it's only stored once in memory. So these are the things you should think about when you're coding and you're using values or pointers. Here's some like a high level syntax cheat sheet here to understand the difference of like when you're referencing variables. So variables have a few different syntaxes that you can use in Go. You can just call the variable name directly, right? And when you do that, you're basically asking the question like, what's in my memory address, right? What's in my box that I have, my memory box? And it gives you the value back. You can also put an ampersand in front of a variable and you're asking like, where is my box, right? What is the address of my memory that my variable holds? And you can also put a star in front of your variable, which is a dereference operator. And all that says is what's in another box, what's in another location memory, because my value has a pointer, please dereference it and follow that to where the actual value stores. So these are the different syntaxes that you'll see in Go. Let's just cover a few pointer gotchas before we move into interfaces. One of the biggest ones is pointers or creating methods with value receivers. So here I have a function called, I have a object person, like it's a structure and it just has an age field, but it has a method at the bottom here called birthday. And that birthday method takes a person as its receiver, but the receiver is a it's a value receiver because it doesn't have that little star in front of it, right? It's not like, P star person, it's P person. So that person object that the birthday method's attached to is a concrete value of a person. And when you have a concrete value, what does that mean? It means that when you call birthday, you're getting a copy of your person structure, right? You're not getting the reference to it, you're getting a copy of it. So when you run this function, you're going to get age 30 printed first, then we'll call birthday, and then we'll print the age again, and it'll still be 30 because the birthday function cannot modify the state because it's received a copy of a person. This is a huge gotcha. I've seen so many people do this in interviews and even in production code where they have some sort of like counter, where they have some sort of state that they want to mutate on a structure, and they create a method with a value receiver. And now you cannot touch that state. So I've seen this happen quite a bit. So just be mindful of that. But if you want to actually mutate the state of a structure, all you have to do is this simple one-line little change. And like if I went back and forth between the slides for a second, you'll see that the slides look exactly the same except for one character in this whole code. And it's that little star character by the birthday function that tells you that the P receiver, right, this person receiver, is a pointer receiver now. So now when you call birthday, you are accessing the person directly. You're referencing it by its pointer, by its address, and you're able to mutate its age field. So now this code will print age 30, it'll run birthday, and it'll print age 31 because the age has been incremented successfully. That's a huge pointer gotcha. The other gotcha is with reference types in Go. So we have slices in Go, which are basically our dynamic list essentially. And you're able to create slices in Go here, and you're able to like pass those slices around to different functions, right? You're passing them around. But slices under the hood in Go are reference types, right? Because slices are basically a pointer into a static array somewhere. So this code's a little tricky. And like, honestly, even me writing this example had me a little confused at first because this is not so obvious. I created a slice here with the numbers 1, 2, 3, 4, 5. And I have this work function at the bottom here that takes a slice of integers. It multiplies all of the integers by 100, but then it also appends new integers to this slice. But when I run this function, I don't know if anyone knows what the output's going to be here, but if I run this function, you would expect that the numbers before I run the function would be 1, 2, 3, 4, 5. And then the numbers after I run the function would be 100, 200, 300, 400, 500, and 600, 700, 800, 900, and 1000, because I'm appending in this work function at the bottom here. And you would think that like that actually makes it to my slice, but it doesn't. When I actually run this code, I get 1, 2, 3, 4, 5 being printed, but then I get 100, 200, 300, 400, 500. I don't see these appends that happen at the bottom, not at all. And the reason is kind of a little weird. In Go, since slices are reference types, you can actually modify the existing elements in a slice. But if you were to do an append operation and add new elements to a slice, the append operation returns a new slice. So even though the work function here receives my nums reference, when it calls append, it has to create a new backing array, and that means it gets a new slice. So my original num slice here in the main function can only see the first 5 elements, and it sees the change to them. So this is a fun little example. I've also seen this happen, especially like in like code that passes kind of like around a queue, right? Or like some sort of slice around and has that slice storing some state. I've seen this happen a lot. So be careful when you're passing around reference types. If it's a map though, it's a little more straightforward. Even though you pass a map to a function, the modifications within are seen by the caller. So in this case, it works kind of as you expect. I have a map up above here that just has a name and an age or whatever. So it's my name and an age 30. Before I run this work function, I print out the map, and it has one element inside. It has Matthew with the age of 30. When I call this work function, I update the Matthew element to be age 99, and then I have another person called Amanda of age 30. And even though this work happened in a function that I called, the caller will still see the effects. And when I print out the map after I call the function, I will see 2 entries, one for Matthew with 99 and one with Amanda with 30. So unlike slices, maps kind of work a little bit more intuitive, right? If you pass maps around in your functions and you modify them, the callers will see it. That's why usually when you're working with maps, especially when you're doing concurrent operations, you're going to want to like wrap that with a mutex, right? So you don't like have concurrent writes modifying things, because all the callers can see the changes. Cool. Let's get into some interfaces now. So now we understand pointers. We know that you can have concrete values stored in your variables. You can then have pointers to those memory addresses for those values. You can dereference them. You can do all these cool things with pointers. We get that. But let's move into interfaces, right? Because interfaces are another concept of Go that many Gophers kind of struggle to understand. So what's an interface, right? That's the question here. What is even an interface? Well, my wording or my phrasing is an interface is just a type that guarantees the behavior of other types, right? And like you're probably asking like, Matt, what does that really mean? Well, an interface is a way to kind of constrain the behavior that you want to see from types. So interfaces define the methods that other types must implement in order to be used as that interface type. We all have worked with interfaces in Go. If you've written even like the simplest of simple programs, you've probably worked with interfaces under the hood and you didn't even know it, right? One of the most common interfaces in Go is the IO writer interface, or its complement IO reader. All this here says is this is declaring a new type called writer. And this type says any type that has this write method that takes a slice of bytes and returns an integer and an error, any type that has this method can implement the writer interface. So if you need something to be a writer, well, then you just have to add this method to that type, and Go will automatically treat it as a writer in the scenarios that it needs to, right? There is no like impl block like you have in something like Rust or implements in Java or whatever it is. You don't have to explicitly implement your interfaces in Go. You get them implicitly implemented as soon as you put the right methods on them. What does that look like? Well, it looks like this. I have a function here called work that takes a writer, right? It takes one of those IO writers. And since this function takes an IO writer, the only method that it can call on that type is write, because the interface only specifies this one method, right? It specifies write. And if I want to take a type that is an IO writer, then the only thing I can do with an IO writer is call write, right? I don't have any other ability to call any other method. I can just call the write method. So here I'm taking the OS standard out variable in Go. I'm passing it to this work method, or sorry, this work function, and it's able to call write. Why does this work? Well, under the hood, os.standardout is a pointer to a OS file, right? And if you were to look at the documentation for the OS file type in Go, you'll see that it has a write method that matches the signature that the IO writer interface wants. The Go compiler is able to see this. It's able to see that, oh, you're passing an OS file to your work function. The work function takes an IO writer, and the OS file has the write method. Boom, that all works correctly. I could have passed a bytes buffer to this work function, because the bytes buffer also has a write method on it that matches the IO writer interface. And this would have worked just as well. Go doesn't care, right? That's the point of interfaces here. I don't care about which exact concrete type you're passing me. I just care that you pass me a type that has the method that I wanted. In this case, the method that I wanted was the write method. You can pass me an OS file. You can pass me a bytes buffer. You can pass me a netcon or whatever under the hood it is. Go will treat it the same, because you've constrained the behavior that you want to be that writer interface. You are guaranteeing the behavior. There's a common quote here in the Go community called accept interfaces and return structs. What does that actually really mean, though? I'll show you in a code example. So again, same code that I had before for the most part. I have that work function that accepts a type of an interface, right? It accepts the IO writer interface. So you'll notice here that I am accepting, my work function is accepting a type that can do write, right? That can do the write method. But you'll notice in the main function, I'm getting OS standard out, which we know is a pointer to an OS file. I'm passing that OS file to the work function, where it's going to be used in the context of being an IO writer. But then after I call work, I'm calling standardout.close. How does this work, right? Because we know that the standard out type is an OS file. We know the OS file has the write method. We also know that an OS file has the close method. But if I pass this standard out object to the work function, I'm constraining it to be just an IO writer. But then after I call the work function, my standard out variable here, it's still an OS file. So I can still access its other methods that aren't write. So you see how the call to the work function constrains the methods that I can call on the type that I pass it. If I updated my work function to take an OS file, I can call the OS files write, I can call the OS files close, I can call all the methods. But since I've constrained it to just the behavior that I want, I can only pass types that implement the interface, and I'm guaranteed to have the right method available to me. But this is all cool. But what happens when something like this happens, where you have some sort of factory function or constructor function that you're building your writers from, right? People that come from Java are like they do this all the time. It's kind of a little frustrating, but they do this all the time. They build these factories that return interfaces, and something like this happens, right? You call your factory to get your writer. You pass your writer around to do all the work, but then you know that the underlying implementation of your writer is a file or is a bytes buffer or something different, and you want to call its specific methods to do other pieces of work. Like in this example, I want to call this close method here because I want to close this file. But since I've constrained my type to be an IO writer using this constructor function here, I've returned an interface from this constructor function. That means no matter what type I return from this constructor function, the Go compiler is going to limit that type to be an IO writer, which means I can only ever call the write method. I've now lost access to all of the other methods that are on this OS file because I've written this constructor that returns an interface. And this is what that quote was trying to get at, where it says accept interfaces, but return structures. And what I believe the author was meaning in that is accept types based on what they can do, but give types that can do anything, right? And let the callers figure out what behavior they really want. So that's like a really good pattern, right? Your functions that you're going to be writing in your code should accept interfaces because that guarantees the methods you can call. But any sort of constructor methods that you have or constructor functions, they should just return a concrete type, because then you give the caller the option to like implement the interface if they want to, right? If I just change this IO writer line here in the middle of the code block, if I just change that to be like a pointer to an OS file, this code would have worked still, and I would have had access to the close method. And this is just showing the same thing for a bytes buffer. Same concept here. I can call the bytes buffer string method, the stringer. But if I had that same concept of like returning an interface for my constructor, I can no longer call the string method. Right, I'm just showing you. I wanted to show you more than one example so you can see that it's not just like the OS file that has this problem. It's anything that follows this pattern will have this problem. But what if I did have the interface being returned from my constructor, but I want it to get those methods back, right? Let's say like I want that stringer method back, even though like I want to keep the code the same, but I still want that string method. I want to be able to get it back, even though my constructor is returning an interface. How can I get that stuff back? Well, pretty simply, I mean, simple is a relative term, but you can do what's called a type assertion in Go. So even if you have an interface type, you can type assert it against any other type in Go and see if that type assertion was successful. And that's how you can get access to those methods again. So if I really wanted to get access to that like OS file underlying type, I can do this OK type assertion idiom in Go. And I can say, hey, Go, please take that standard out interface type that I have, try to type assert it back to a pointer to an OS file. If you can do that, great. I know this is an OS file. I can call its close method. So if you really, really couldn't change your constructor functions to like return the concrete type and you had to like deal with this sort of behavior, you have kind of an escape hatch here and you can do type assertions to get that behavior back. Now, mind you, the whole point of interfaces is to provide that abstraction through the methods that you want, right? That behavior. So if you do this, you're kind of like breaking that abstraction a little bit, right? Now you care again what the concrete type is, and you no longer just care about the behavior. So just keep in mind when you're doing this stuff. And this is the same example, but doing the type assertion on the bytes buffer to get access to its string method. One last thing about interfaces before I close up. There's a type in Go called the empty interface. Before Go 1.18, I don't remember when any was introduced, but at some point there was a type in Go called the empty interface, and it was just like interface with squirrely braces or whatever. But there's this new type called any, and it's just the empty interface, right? This is I think this was Go 1.18 when they released the any type, whatever. Either way, there's a type in Go called the empty interface, and it is an interface that has no methods, right? So it's a type that says any type that has no methods can be an any type. I know that's a little bit of a tongue twister, so I'll say it again. Any type in Go that has zero methods has at least zero methods can implement this any type. Well, we know that every type in Go has at least zero methods. So every type is any type, technically. So what does that mean? That means if I use this any type in my Go program, I can assign it an integer. I can assign it a string. I can assign it a pointer to an OS file. I can assign it any one of these types because all of them meet the specification for having at least zero methods, right? Because when you use this any type in Go, you're saying, I want anything, right? I want any behavior. That's what you're doing here. That's why when you see like map string any's, that's why it works with any sort of type, because every type implements the any interface. So now that you know what interfaces are, and now you know how they work under the hood, you can now look at this any and be like, oh, I get it now. Cool. Let's just quickly recap the interface stuff, and then I'll open up to questions. So what does all this mean for me as a gopher, right? Now I know about interfaces. Why do I care about this stuff? Well, you care because the usage of an interface guarantees what a type can do, not what a type is, right? In the examples that I gave you, I asked for an IO writer. I don't care if you gave me an OS file. I don't care if you gave me a bytes buffer. I don't care if you gave me a strings reader or a strings buffer or whatever. I don't care if you gave me a net.conf. I don't care what type you actually gave me. As long as it has the behavior of being able to write, I can work with that type, right? And we use interfaces every single day of our lives, right? You don't care what type of door you're going through. You just care that it can open and close, right? That's literally the behavior that you want. I don't care if it's a wooden door, if it's a steel door, if it has 30 hinges, 0 hinges, 1 lock, 3 locks. You just care that it opens and closes. And it's the same thing in your code, right? You just want to care about the behavior so that you can code against that behavior. And when you do that, you get all of these beautiful things for free. When you're designing with these interfaces, you're able to enable polymorphism, right? Allowing code to do more than one thing. You're also able to now mock in your tests. Now, when you have an interface that says, I want to be able to write, or I want to be able to notify, you can make mocks for that do mock notifications and mock writes, just because you define the interface type. This is very similar, like with there's a couple talks at, excuse me, in like past GopherCons that talk about using AWS APIs, and if you have like a raw pointer to an RDS database or something, that you can call these methods. But if you make an interface type that has those methods, you can mock it. That's what you get when you use interfaces. You get the behavior that you're looking for. So in production, you can pass the real concrete type that you want to use, but in testing, you can pass like the mocks. If you did want to retrieve those underlying methods that you lost because you constrained yourself to an interface, you can always get them back by using those type assertions that we talked about. And now these last 2 quotes here, one I already covered, but you should be able to understand what these mean. So accept interfaces return structs. Now you understand that your code should accept things based on what they do. You don't care what underlying type it is. You should just accept things based on what they can do. And if you're building those constructors, you should return the concrete structure and let the callers figure out, if they want to constrain it with interfaces. And then the last quote I'll leave you with is, don't design with interfaces, discover them. That's from Rob Pike. What he means here is, when you're coding, you should always start by working with concrete types, right? In this example, you saw me use an OS file or a bytes buffer. If you need to be able to like write data, use a concrete type, right? Use the OS file, use the bytes buffer. And then as you like create a couple of implementations that write data around, you will find the commonality of the behavior you're looking for. You will find like, oh, I actually don't care if it's a file or if it's a byte buffer or if it's a connection. I just want to be able to write, and boom, that's your discovery, right? When you start to think about your programs and you start to realize like, oh, I don't really care about the type anymore. I just care about the behavior. That's when you know you're at the point where you've discovered an interface. And that's when you can like refactor your code to use interfaces. Cool. Here's some additional resources that y'all can read to get some more information here. I read all of these. They're really good. The first one is where the quote from Jack comes from, to accept interfaces, return structs. And then the bottom 2 are more like just deeper dives on how interfaces and stuff work and go. And that's all I had from you. I hope you enjoyed it, and I will definitely open up for questions now. I'm watching YouTube chat too, by the way, so if anyone's there.
So thanks for the chat. It's very informative. I have a quick question, because you mentioned escape analysis.
Yep.
So is that something that you do often when you're programming? Is that part of your workflow to do escape analysis, or is that something you don't do it unless you need to check for memory usage?
Correct. I the latter. I only do it when I'm like performance optimizing, right? Like if there's a problem, then I'll do it. I don't really like go my day-to-day coding and worrying about it too much. Like it's kind of in the back of your head where like, oh, that's gonna allocate or not. But it's not something that I like worry about until it really becomes a problem.
Okay.
And that's when you do like your benchmarking and your profiling and whatnot.
Okay.
Any other questions from the chat? or from people that are on the Google Meet live?
I don't see any other questions. So.
Oh, and I wanted to ask you, because you're going to be at GopherCon, Matt?
Yeah, I'm going to be at GopherCon US in Chicago in like what, 2 weeks now? I don't even.
Okay.
Yeah, like 2 weeks. Yeah.
Okay. And you're doing the lightning talk, right?
Yep, I have a lightning talk there. So if y'all are going to be in GopherCon US, feel free to drop by lightning talk. I'm going to be talking about some of the Go tooling that we have and like, you know, how Go relates to like how software engineering really relates to like the house renovations that I was doing.
Okay.
I also have a question. I know that you also have a talk regarding choosing Go for a technical interview.
Yeah.
Do you know when you will have an opportunity to deliver this speech? I think it's an interesting topic for, I don't know, aspiring golfers which want to land a Go job.
Yeah, I can definitely give that talk as well. I have that talk already, like there's slides for that and everything's ready to go. I gave that talk at a in-person meetup in New York like a month ago or 2 months ago. So I'll be happy to give that talk. It's another fun one where you show like code examples and how they affect your program.
Okay.
Oh, I see the chat. Thanks for digging into behavior. I think we lose track of the details and fall into habits. Yeah, a lot of people, they skip right into like habit-based things. And that's okay if you're like experienced and you know what you're doing. But to a lot of like newer gophers, it's not obvious sometimes. And I think just taking this time to understand, you know, what it really means to have a pointer to something and what it really means to have an interface, it really, really helps, you know? And we've all probably been there where you're working with code and there's so many interfaces that it gets difficult to find the real implementation that you're working with, you know, and maybe your editor set up correctly and you can like go to the implementation and all that, but it can get difficult to follow some of the interfaces around. So just knowing, even just knowing what that means allows you to at least look for other types that implement the interface. Cool. I'll give it another minute or so for any questions or comments. I know the live stream is like slightly behind. Not so bad though.
Yeah, I think there are 15, 20 seconds. I tried to measure this.
Yeah, it's not bad.
Is there anything else that we didn't ask you about that you want to mention before you end things?
The only other thing would be there's like a compile time interface assertion that you might see in Go where you like, I don't have the code the code in front of me. I'm trying to get an example real quick. But basically, if you're like an author of Go code, you'll probably see like something like this. I'm gonna post it in the YouTube chat.
Okay.
You'll probably see something like this: IO writer, and then my custom type. You'll probably see something like this in the source code somewhere. And this is a like, I guess I got an error sending that chat. Here, I'm gonna put it in the Google Meet so you can all send it.
Okay.
Because
we can send it out later.
Yeah, I threw it in the Google Meet. Feel free to put that in the YouTube chat so people can see what I'm talking about.
Yes, adding it now.
Yep.
It's in the chat.
Thank you. Yeah, when I sent it, the chat gave me like an error. I was like, okay. But anyway, you'll probably see something like that in code that you're either writing or managing or whatever. And this is like what we call the compile time assertion for an interface. And all this is saying is it's constructing like a zero value of your custom type here, right? Whatever custom type you have. And it's making sure that that type can successfully be assigned to an interface. And I've had arguments with like engineers about this in the past of whether or not this should be a thing, but I find this helpful because if somebody like if somebody that's like not as experienced goes and changes like the function, the method signature for a method on your type somewhere, they can break implementing your interface. This is one of the negatives about Go interfaces, whereas like Rust has like the impl keyword where you can like explicitly implement an interface. Go doesn't have that, right? All the interfaces are implemented implicitly just by putting those methods on your types. So if somebody comes along and they change your write method, and instead of taking a byte slice, it takes a byte slice and a context or something, right? They've just broken the implementation of your interface. And that's a problem. And if you don't have any sort of checks for that in your code for compiling or whatever, you can ship that to production and it'll break. So something like this can be used as like a little like, it's just a little bit of defense, right? Kind of like that defensive coding that lets you know, because this will have a compiler error the second you change that method and break the interface implementation. So I don't know, that's something that I like to see sometimes, just because it's very explicit and it's a really good way to kind of like make your intention known. So I kind of like to put that right above the type, and it shows me as the coder like what I'm trying to implement. You know, it's a little bit, it's kind of like one step greater than a documentation comment or something, because it'll result in a compiler error if it breaks. So yeah, that's the only other thing that I didn't cover.
Okay. I think we're ready to end it then. If we've had no more questions.
Yeah, I think we're all set. Yeah. Thank you all so much for having me.
That was really amazing. Very informative. It's things that if you're new, you need to learn, and if you've been using Go for a while, it's just good to refresh as well, right?
And for me personally, I'm still learning my interfaces, so it was a very educative session.
Yeah, that's what I hope. Yeah.
And also, I'll keep an eye on you when you do the choosing Go for a technical interview.
Yeah, definitely. I'd be happy to give that talk. That one's a fun talk because it's pretty relevant to the job market right now. And I do a lot of interviews every week, so I see a lot of little gotchas that people make when they write Go.
Yes, I think this is a very hot topic for people searching for Go roles.
For sure. If anyone likes video content, I have another YouTube video coming out soon about interfaces in Go that walks through like a more live code to show you like kind of how to refactor things and get interfaces working. So keep an eye out for that. And yeah, thank you again for having me. I really appreciate it.
Very amazing. Awesome. Thanks so much.
Awesome. Thank you very much. Bye-bye.
Bye, everyone.
See you.